So maybe I'll just write down what we proved last time. So the first theorem. Okay, so this is what we proved. So let G be a fine. Okay, let me just make a state. P prime number that divides the order of G, okay, and write order of G as P to the E times M, where P does not divide M. Okay, so this is how. Okay, so this is up. And so the first theorem, there exists a subgroup of order P to the E. G has a subgroup of order P to the E. Okay, so just want to introduce a definition. Subgroups of order, subgroups of G of order P to the E, where, I mean, this is a finite group, okay, where P to the E divides the order of G and P to the E plus 1 doesn't divide. So this is the largest power of P that doesn't divide order of G, okay, are called P, called Silo P subgroup, not P Silo P subgroup of. So what is saying is that there is something called a Silo P subgroup for every finite group and every P dividing. This is the maximal, I mean, P to the largest power, the order of the subgroup is the largest power that divides the order of the group. Largest power of P that divides the order of the group. Okay. So, okay, so yesterday, I mean, on Tuesday, we proved the first theorem that G has Silo P subgroups. And as a corollary, we can reprove Cauchy's theorem, Cauchy-Lagrange, Cauchy theorem. G has okay, so this is so you first proof. So take a Silo P subgroup. So let H be a Silo P subgroup. Subgroup. So then order of H is greater than 1. So pick X inside H, X not equal to 1. This implies that there exists some J such that X to the P to the J is 1 and X is not equal to 1. I mean, the order of X is, we should just write more. Okay. This implies that order of X is P to the J for some J greater than or equal to 1. It's at least P. The order of X is at least P and a power of P. Okay. So then the subgroup generated by x to the p to the j minus 1. So the j minus 1 is the exponent for p, not p to the j minus 1. Okay? So this whole thing is on top. Okay? Has order p. So yeah, so one can derive this theorem as a consequence of Cauchy's theorem, of Sloth first theorem, but also, or as we did earlier, we could prove it directly. But in any case, both of these proofs use some idea of group actions. Once we understand the idea of group actions, neither of the proofs are particularly difficult. I mean, the difficult part is to come up with a set and the group action to conclude the necessary conclusion. But one there are various choices for that. So this is the first theorem. Yeah. Okay. So now second theorem. Second and third theorems I'm only going to state and try to use it in an example. So my plan after so I got 15 minutes late, so I may not be able to do everything that I meant to do today. But my plan is to do groups of order 15, which will be worked out using zero theorems. Then groups of order 8, which one does not need zero theorems because it's already a power of p, power of 2. Right? Zero theorem is unlikely to help there. So that requires that's mostly some sort of hand calculation. So I will that's the plan for today. If I am unable to finish the group of order 8, I will put that as it. So I'll okay. So sorry, I should just clarify. So next Tuesday is a CMI holiday, so there will be no quiz, no class also. Okay. Whatever about group theory I want to finish today. So there might be some leftover work about groups of order 8, which I will outline in an exercise. So it shouldn't be. It is not very difficult. Once you see what sort of calculations have to be done, it is sort of just sort of straightforward checking those things. Okay, so I'll outline there if I don't finish it today. And so next Thursday, I hope to finish it in one lecture itself, a discussion about quotient vector spaces, which is okay, so I'll try my best to finish, to not take an extra lecture. So that's the plan for next week, or today and next week. So second theorem. So again, same hypothesis. Okay. G is a subgroup. G is a group, finite group of order, and P is a prime number that divides, and P to the E is such that P to the E divides the order of the group, and P to the E plus 1 doesn't divide. Okay. So part A. Okay. So G, P, etc. etc. First statement. Okay. The Silo subgroups, Silo P subgroups of G are conjugates of each other. One. Okay. So that means if H and H1 and H2 are two subgroups of order P to the E, then there exists a G such that GH1 G inverse is H2. Okay. So this is a somewhat very strong statement. There are certain subgroups of certain order in the group, of the same order in the there are two subgroups of, two of some specific order, subgroups of some specific same order in the group G, and they are conjugates. Okay. So this does look like a strong statement. A priori, otherwise a group can have, even consider It's not very difficult to come up with examples where there are subgroups of the same order and they're not conjugates of each other. But here, in fact, in a abelian group, for example. So here it is a very this is a strong statement. And B, so here is the, so every subgroup of G that is a P group is contained in a silo P subgroup, meaning in other words, so let me just clarify what this means. In other words, if H, order of H is, H is a subgroup of G, and order of H is a power of P, then there exists a subgroup H1 of order P to the E such that H is inside H1. Some silo subgroup, of that P. So again, so this is the second statement. So let me just, I'm not going to prove it. I will just say, what will be proved, or which will imply both these statements, but not get into the proof of that. So the first thing says that silo P subgroups are conjugates. So of course, by definition, they are of the same order, and then they are conjugates. Second thing says, if you have any subgroup of G that's whose order is a power of P, then it is contained in a maximal subgroup of that order, which has power order P to the E. That is, H1 has order P to the E. So this is this statement. So as I said, I will not. I don't want to. I don't want to prove the statement. Proofs are again setting up clever group actions and inferring these things, but it is sort of time consuming. So let us concentrate on learning to use these in some extremely basic examples. Maybe. Yeah, I suppose one would need a full course on finite group theory to get into the great details of these things. This is we're sort of out of time. Okay? So what so statement which will be proved. Okay? So to prove these two statements, so this is a statement. One proves the following. Let H be a subgroup of G. Okay. That is a P group. And H tilde be a silo P subgroup. Then there exists a G in G such that G H G inverse is a subgroup of H tilde. Okay, so again, this isn't. This isn't simplifying the statements, but this is the. This is a statement which will imply both A and B. Okay? This will imply A and B. Okay, so to get B from this, So there we want to show that H is contained in some CLOP subgroup. This take H1 to be G inverse H tilde G. Okay. So if there are two subgroups, I mean, if a subgroup and a conjugate subgroup has the same cardinality. Right? So therefore, if H tilde, since H tilde is a CLOP subgroup, it has order P to the E. Therefore, the conjugate thing G inverse H tilde G also has order P to the E. Okay. So this thing has order P to the E. So this is a CLO subgroup. So if we take H1 to be this, then this would satisfy. So if we prove this statement, this thing here, then that would imply B by just this that trick. Okay. Now to get A from this, to get A, sorry, just a minute. To get A, so then we need to show that if the two CLOP subgroups are conjugates of each other, okay, take H to be a CLO subgroup. So this implies that G H G tilde G inverse is inside H tilde. Okay. They both have the same cardinality, since order of G H G inverse is equal to H tilde, G H G inverse is equal to H tilde. This is okay. So this statement proves both A and B. Okay. So, but but yeah, proving the statement itself is will take maybe half an hour at least. So we will not be able to do any examples. Okay. So at least, okay, so I'm trying to at least give some picture of how these things proceed, okay, without actually getting to the details. Okay. So one has an immediate corollary to this. Okay. G has exactly one CLOP subgroup. If and only if the CLOP subgroup is normal. Okay. So G has at least one CLOP subgroup, and if that number is 1, then if you try to conjugate it, it would be another CLOP subgroup, and but then you will not get anything new, so it is normal. Conversely, if it is normal, then there can't be any other. So proof if so if so if so let okay, maybe let me just so let maybe if so let H be CLO P subgroup that is normal. Okay. Let H1 be any CLO subgroup of CLO P subgroup of G. Okay. Then okay, H1 is conjugate to H. That is, there exists G such that H1 is GH G inverse, but this is equal to H by normality. That proves that there is only one zero subgroup, and only if. So we need to show that if it has exactly one closed P0 subgroup, then it is normal. So let H be the only Silo P subgroup of. We want to show that it is normal. So let G be inside G. Then GH G inverse is a Silo P subgroup of G. Therefore, GH G inverse is H, and that is so that is H is normal. Okay, so this is a corollary that if for some P there is a unique Silo P subgroup, then that subgroup must be normal, and converse is also true. So this is the second Silo theorem. And the third thing now says how many Silo subgroups there are. Okay. So third theorem. Sorry, any questions on this so far? I'm sorry, I in the interest of time, I have to skip the proofs, but we will try to understand at least how to use it in some examples. Okay. The number, so again, the notation is the same, G, P, E, M, etc. as above. Then let S be the number of Silo P subgroups of G. Okay. So we said that there are Silo P subgroups. There is at least one, and they're all conjugates of each other. And let S be their number. Okay, some finite number, because G is a finite set. It has only finitely many subsets. Okay. So S must be finite. Okay. Then F divides M. Remember, M is the index of the P Silo subgroup. Silo P subgroup. Silo P subgroup's order is P to the E, and the index is M. Okay. The number of cosets is M. S divides that. Okay. And S is congruent to 1 mod P. So so for example, it is not saying S is 1. Okay. But if S is not 1, then S is at least P plus 1. Okay. And if it's not that, it is at least 2P plus 1. Okay. So there is some, there are some restrictions. From this, sometimes we might be able to conclude that S is equal to 1, and therefore we now have a normal subgroup. Okay. So that's how many arguments will proceed. Okay. So this is the okay. So this is the third theorem. Okay. So I will not. I won't get into the proof of any of these statements because this requires a little bit more working, because you have to say that S divides M. So some cosets and etc. have to be there has to be some action, etc. Okay. So I won't. Yeah. So let me not. Okay. So let us do an example. Again, this is from the book. I have skipped the longer example of 21, which is, and yeah, so the book discusses three things: 15, 6, and 21. 6 we have already done through some specific calculations. We know what order groups of order 6 are: cyclic group and the permutation group S3. Okay. This we identify, which is also equal to the dihedral group D3. Okay. So this is something that we have done. So I don't want to repeat that calculation, but it is worth. I mean, you should read that thing in the book to understand how it's proved using zero theorems. Okay. We did it with some explicit calculations. Assume that there is an element. I mean, first of all we remove the case that there is an element of order 6. Okay. Then there is some element of order 2 and element of order 3. We proved. I mean, you know. And then we sort of ruled various things out, and that's how we calculated this. But this is a different proof, and you should read it, how it is proved using zero theorems. But I'm just going to do it for 15. So as I said, I will do two examples: groups of order 15 using zero theorems, and groups of order 8 without using any of these things. But it is good. So let G be a group of order 15. Okay. So by zero theorems, there is a subgroup of order. There are 3. So this is 3 times 5. So there exists a subgroup of order 3. Let us call this thing H, and a subgroup K of order 5. Of course, this statement alone we could have figured out as soon as we proved Cauchy's theorem. We don't need to wait till zero theorems to do this, but this is what we have. Okay, so now, so this is from, so I'll just write here from Cauchy's theorem slash Silo first theorem. This is what we have. Okay. So now, so how many such H's are there? I mean, groups of order 3. Okay. So let S be the number of Silo Silo 3 subgroups. Okay. So then, by above, by the third theorem, S should divide the index, which is 5, and S should be 1 mod P. Then S divides 5, and S is 1 mod 3. Okay. So S is 3. Okay. That is this. That is H. The H that we have identified, called the is normal. Sorry, S is 1. Okay. And we observed earlier that if for some P there is a unique P Silo subgroup, then that subgroup is normal. Okay. Okay. So similarly, okay. So now, okay, so let S1 be the number of Silo 5 subgroups. Okay. Then S1 divides 3, and S1 is congruent to 1 mod 5. So K is normal. Okay. So we have now identified there are two subgroups: subgroup of order 3 that is normal. I mean, that is normal, and subgroup of order 5 that is normal. Okay. So these are all the Silo subgroups that we have. So now we need to prove a slightly useful lemma. Okay. So H intersect K. So suppose that. So let G be inside H intersect K. This means that order of G divides 3 and 5, which means that order of G is 1, that is, which implies that G is 1. So that is H intersect K is the subgroup generated by 1. That's all. So now let us prove a useful proposition, which of course we could have proved a long time ago, but this is a point where we can actually use it. Okay. So now we have identified two subgroups, which is an intersection is trivial. So proposition. So this is 2.11.4 in the book. So let H and K be subgroups of G, and let F from the Cartesian product, just a set, H cross K to G, be the function F of H K equals H times K. Okay. So this is not a group homomorphism. Okay. This is just a function. Then okay, 1. F is injective if and only if H intersect K is just 1. 2. F is a homomorphism, is a group homomorphism from the group. So here, let me emphasize here, I mean this only as a set. Okay, I'm just thinking of this as a function from a set to another set. Now I am making a statement about it being a group homomorphism from the group H cross K to G. So if and only if elements for all K in K and for all H inside H, KH is equal to HK. It is not saying the group is abelian. It is saying elements of K commute with elements of H. K itself could be non-abelian and H itself could be non-abelian, and which would force G also to be non-abelian. But elements of K commute with elements of H. Okay, so this is what. Okay, so 3. If H is a normal subgroup of G, then then HK, which is by definition things of the form H times K, H is inside H, K is inside K. Just take the products. Okay? Don't. Okay? It's a subgroup of G. It is bigger than, it is potentially bigger than H, but it's okay, and for, so this is where what we need to use. Okay, F is an isomorphism of groups from the product group. Maybe I should, I think we only sort of informally said what this product is. So I clarified this now to G, if and only if. Okay. So if this happens, then H is a normal subgroup of G, and this product will be a sub thing. Okay. So if and only if, first of all, it has to be injective. That's the first condition. The product group is, I mean, this not product group, this product HK is G, and K and K and H are normal subgroups. Sorry. Let me just use this week. Okay, okay now. Okay, yes, so yeah, so since I'm okay, so let me just actually not, I was going to prove this and then use it, but I realized that if I do that, this will take more time than I thought. Okay, so let me just, okay, so for us, in our example, order of H is 5, is 3, order of K is 5, their intersection is 1. This means that the map F is injective. Okay, so this, so let's look at the condition which says it's an isomorphism. So for that, so this condition is required that establishes injectivity. Okay. Then the product group is G. So what is this H? Not product group. The product, the set HK. What does it? It is just saying this thing, okay? And that is just the image of F. Okay. Note that the image of F is the set of all HK such that H is inside H and K is inside K. Okay. This is what we denoted by HK. Okay. Since F is injective, order of, I mean, the cardinality, this is not necessarily a subgroup. This cardinality is 15, which is also equal to the order of the group G. So these two are the same. HK is a subset of G, and they're the same cardinality, so they are the same. I mean, that is they're the same finite cardinality, so they are the same. Okay. So this checks the second condition, and they are normal subgroups also. We've already seen that H and K are normal subgroups. Okay. So G is isomorphic to the product H times K. Okay, so maybe let me just take a. Okay. So what is G cross G2s? Okay. So the underlying set is the Cartesian product. The Cartesian product of sets. Okay. The operation. Okay. So we have some G1 comma G2 times G1 prime comma G2 prime. Okay. This is, we define it to be G1 prime, G2 prime. Okay. So this is the definition. This is being defined. This product is in G1, and this is in G2. These are given. What is the operation on G1 and what is the operation on G2 is given. So we can individually do these calculations, and we say that that is the product of this pair with this pair. Okay. So this is the this is how it is defined, and then one checks that. Okay, check that E of G comma E of G1 comma E of G2 is the identity element. I mean, check that it is associative. Then I mean, check that one. This is 2 associativity identity element, and 3. If you take the pair G1 G2, its inverse is G1 inverse G2 inverse. So the individual inverses are calculated in the given groups. Okay. So therefore, so this is the product group. Okay. I mean, we have earlier done what is Z2 cross Z, Z mod 2Z cross Z mod 3Z, etc., etc. This is just a. Okay. So this is what we have. Okay. So another observation is, since H and K are abelian, since H is isomorphic to Z mod 3Z, because it's a cyclic group, I mean, it's a group of order 3, and K is isomorphic to Z mod 5Z, H cross K is abelian. Okay. Therefore, every group of order 15 is abelian. We want to make a slightly stronger claim. So let H inside H be a generator of H, and K inside K be a generator of K. Okay. Then HK, the order of HK is 15. So that is because okay, that is because they commute with each other, and the reason is so if you take HK to some n, okay, this is equal to H to the n, K to the n, okay, and their intersection is trivial. So if this is equal to 1, would imply that H to the n is 1, and that is also equal to K to the n, okay, because this element is inside both H because it is 1, and it's, maybe I should write it here. Okay, and the only element that is inside, because okay, so remember h to the n is inside h, 1 is inside. Maybe this implies that h to the k to the n, which is h to the n inverse, is inside h. This implies that k to the n is 1, because that's the only intersection with k. Okay? Similarly, h to the n is 1. Okay? So 15 divides n, which implies that n is 15. And they're not, I mean, n is not 1. It is at least, it has to be divisible by, I mean, n is not 0. Okay? This is not right, okay, or 1. So it has to be divisible by 3 and 5. So it has to be divisible by 15. Okay? So this implies that 5 divides n. This implies that 3 divides n. So 15 divides n. So n is 15. It can't be more than 15 because the group has only 15 elements. Okay? Okay? So therefore, G is cyclic of order 15. Okay. Sorry, this example itself took longer than I had hoped. That too without proving the key proposition that helped us establish this isomorphism. So maybe I'll just stop here, because I have some 7-8 minutes and I won't be able to do anything. I mean, I see that it is easy to identify so I wanted to do the groups of order 8. Okay. Maybe I'll just list them without actually any proof. Okay. But just out of curiosity, no particular. Okay. I wanted to sketch most part of it, but I don't think I will. Okay. So what are the possible abelian groups? Okay. There is a cyclic group. So if the group has an element of order 8, it must be cyclic, and it must be this. Okay. It can have order 2 or order 4. Or, I mean, elements can have order 2 or 4 or 8. Okay. So we have ruled out the 8 case. This is if and only if so G is isomorphic. There exists G in G of order 8. Okay. If so, this is one case. Second, another case is if order of G is 2 for all G in G but not the identity element, then we have seen that G is abelian. Okay. And moreover, okay, and so in this case, then one can show that it is also isomorphic to Z mod 2Z cross Z mod 2Z cross Z mod 2Z. Okay, so those are two. Okay. Given the unproved proposition that we just used, okay, there's another option, which is, or the ideas behind the proposition, not exactly using that proposition. Okay. Z mod 4Z cross. So first case is there is an element of order 8. Next case is, I mean, G is abelian, and I mean every element is order 2. I mean every non-identity element is order 2. So we get this. Okay. The next case is there is an element of order 4 and G is abelian. So I'm assuming G is abelian for now. Z mod 2. So this is if and only if G is abelian and there exists an element of order 4 and there does not exist an element of order 8. So this lists all the abelian subgroups, okay? Non-abelian. So there is a group that we have not yet seen, which is why I cannot prove the statement. So if I'll just stop it here, I'll just define the group. Okay. So of course there is one that we have seen, okay, D4. So this is permutations of the symmetries of a square. So this is dihedral. Oh, sorry, this is only 4. Okay. Now there is another group called quaternion group. Quaternion group. Okay, so we have not seen this, and we have to actually prove that if it's non-abelian and not a dihedral group, then it must be this. So that requires some bit of calculation, which I just want to mention these things. That's all. Okay? So think of these as the following. Okay? Identity so think of, okay, so let's call this thing H. So this is plus or minus the identity matrix. Okay? Sorry, I forgot. I need to look up the signs in this. Just a minute. I got to look up the signs of. I mean, I know it has to involve some I. Yeah. So plus or minus I 0 0 minus I. Okay. Then plus or minus 0 1 minus 1 0. Then plus or minus. So there are 8 elements of this thing. One needs checking that this is actually. Okay. So. Okay. So the point is that every group element here. So I shouldn't say that. Okay, let me just label these things. Call this, of course, I 1. Okay, I'll call this I. Okay. This matrix and this element I'll call K. So then I to the 4 equals j to the 4 equals k to the 4 is identity. Okay, that one can sort of easily check. For example, I square would be -1 -1. 1 more square would be 1 1. So that is. And then okay, so that one can actually. So then one has to check that this is actually a subgroup. Okay? And this has 8 elements. GL2C. Okay? And has 8 elements. And it's non-abelian. Okay? And yeah. So okay, and this is not isomorphic to default. Okay? So that requires by looking at the order of the elements I square, j square, k square, etc. And so that's how it's proved. But in the interest of time, I will skip all those things. Okay, so this is the theorem is that these 5 exactly are the groups of order 8. Okay? It doesn't use any Silo theory, but I thought, and this is a number that we had left out earlier. Okay, so we did 6, 7, and 7 is fine. 9 was essentially an excess. I mean, it was a proposition which I assigned as a reading p square. Okay, so 15 is, 8, 12, 15, etc. are the sort of difficult things, or the not so obvious things. And so I just wanted to finish this 8. Okay, so I'll stop here. As I said, next Tuesday there's no class or no quiz, and on Thursday I will just lecture about quotient vector spaces, and hopefully I will not need an extra lecture. So I'll stop.
Sir?
Yeah.
Will we have another quiz like the week?
No, this would be the last quiz would be the last one, the one that we just finished.
Okay.
Yeah.
Thank you, sir.